So in the last video, we were able to accurately predict the experimental structures of various AH3 molecules. Let's do something a little bit different this time. Let's look at a series of isoelectronic molecules, all have 8 valence electrons, and look at their bond angles. And the other thing to say is there's an interesting property of trigonal pyramidal molecules, which is that they can undergo inversion, okay? And how are they going to undergo inversion is they're going to go through a a transition state that is a planar molecule. And so we know that all these 8 electron molecules are most stable as the trigonal pyramidal, but if they want to go under inversion, right, they're going to have to go through this planar transition state. And you can visualize this as an umbrella flipping inside out, right? That's exactly what's happening. For a second there, the umbrella is going to be flat before it flips, to the other way. Can't flip my hand that way. Can't turn my hand inside out, fortunately. But anyway, so this is inversion. And, if you wanted to figure out the energy difference between going from a flipped umbrella to a non-flipped umbrella, right? You just need to figure out the difference in energy between the planar and pyramidal MOs, which you can see we're in a very good position to do because we have the molecular orbital diagrams for both the Walsh diagrams, right? And so I've also listed here the inversion barriers in kcal per mole. Something to note here is that obviously the lower the inversion barrier, the faster that this process is going to happen. And so you might want to think about, how could you figure out the rates of these things? We can go over that in class. If you don't know how to do that, that might be some good thing to go over in class. But, for the purposes of this lecture, right, obviously lower rates are going to be faster, lower barriers are going to be faster, and higher barriers are going to be slow. And so for the hydronium ion and ammonia, these are going to be very fast at room temperature. So you're going to have this umbrella flipping happening a lot, this inversion. But for these other molecules, phosphine, arsine, and this sulfur analog of hydronium, those are going to be very, very slow at room temperature, okay? And so you also see that there's this increasingly pyramidal preference, right? So like arsine has a very short bond, very low bond angle, much lower than much lower than 109.5, right? And so this is telling you have a very strong preference to be pyramidal. That then correlates with this, very high inversion barrier. It really doesn't want to be planar. And there's an interesting ramification of this, right? For those of you who kind of know about organometallic chemistry, you might know about that phosphines are chiral. Phosphines that have 3 different substituents, 3 different R groups, for example. Like Grubbs catalyst, that's a very used in olefin metathesis, Nobel Prize winning catalyst. That catalyst uses a chiral phosphines. There's a lot of different chiral phosphines that use this. But, ammonia, you never hear about chiral amines, right? And that's because, yes, they are technically chiral, but you can't separate it into 2 enantiomers, right? Because it's just going to go from 1 enantiomer and then flip, do the umbrella flip and invert and go to another enantiomer. So they're not really useful, at least at room temperature, right? So, the chiral arsines and phosphines are widely used in inorganic chemistry, organometallic chemistry, for particularly asymmetric catalysis, okay? So this is why it's a direct manifestation of this. All right, so in the next video, we're going to rationalize this bond angle trend that we've been talking about.